Hi. This rather dramatic photo from a metal mine shows the consequences of uh, getting slope stability wrong. Where we have engineered slopes, whether that's a relatively temporary one, as in an open cast mine like this, or a slope we want to have as more permanent, for example, in a cutting for a road or a railway, it's crucial that the slope being dug out, the slope being engineered, is stable. And it's a key job for engineering geologists to assess the stability of slopes like this and then to engineer a solution that makes them stable. What I want to do today is to look at some examples of different slopes and their geologies to try and make these assessments, to try and put ourselves in the shoes of a geotechnical engineer. Now, there are many of my ex-students who work in this field and earn a good living uh, dealing with uh, issues like this one. Okay, for this lesson, you're going to need your slope instability handout that's got 4 different cross sections through different geological situations. Okay, let's go. So, if we think about the factors that can affect the stability of a slope, first of all, we have done some preparatory work um, for this in a previous lesson. So, obviously, we need to think about the angle of the slope. The steeper the slope, uh, the lower the chance of the stability that slope being stable. Gentler slopes are far more likely to be stable. However, angle of slope is often dictated, as in this photo, by the topography of the area and also perhaps the money available to deal with a slope. Cutting back a slope to a very gentle angle consumes a lot of land and with it an awful lot of money. The next one is lithology. There are some rock types that uh, are going to be far more stable. Perhaps, for example, uh, a, um, a very solid igneous rock, well cemented sedimentary rock. There are others, though, clay, for example, that can be really difficult to deal with because of its low shear strength. Um, it makes it very weak. The strength of any rock is also going to depend on how weathered it is. Granite might be extremely strong, extremely competent rock. Yet if it gets weathered and the feldspars in it start to break down to clay, it can become very weak, very unconsolidated. Competence of the rock. How does it resist changes in its shape? Um, the example I gave before of the clay. Clay can deform if it can flow because of its low competence. With any engineering issues in geology, we must always consider the water. Groundwater has a massive impact on the cohesion of unconsolidated sediments. If that groundwater is under pressure, particularly, that pore water pressure can separate um, uh, different units of rock uh, and lubricate them. It's crucial to know what's going on with groundwater. And remember, of course, groundwater can change seasonally. You can have higher groundwater levels and therefore higher pore water pressures during the winter than you will do in the summer, perhaps where the water table will be lower. Tied in with that is the amount of rainfall. How is the groundwater recharging? Vibrations can have an effect as well. Earthquakes, even small ones, can act as triggers of mass movement events. How vegetated the slope is. Vegetation can help hold an unconsolidated slope together. and a really important idea, this idea of discontinuities, planar weaknesses within uh, the rocks that we have. The presence, the dip, the strength of these discontinuities is key. And we summarize these ideas about the strength of discontinuities by talking about an idea called the basic friction angle. Now, there's a different video which explains basic friction angles. But to put it simply, the basic friction angle measures the maximum angle at which a slope will be stable. Beyond that angle, if it's steeper than that angle, the slope will fail. If it's lower than that angle, the slope is stable. It brings together lots of these different factors in a simple measure. Let's try and put this into practice. Let's look at some examples to illustrate this idea of discontinuities and the basic friction angle. If we look at example A, clearly is a block that has the potential to slide down the slope. Now, the reason for that is we have clear discontinuities within the rock. We have a direction that block of rock could slide. And these discontinuities appear in the engineered slope. This is what we call daylighting into the slope. So there is potential for this to fail, for this to move. If, though, the basic friction angle of the rocks shown in these diagrams is 26 degrees, the dip of that potential sliding surface, that discontinuity, is less than 26 degrees. Therefore, the friction along that discontinuity is greater than the force acting down that dip slope. So therefore, example A here would actually be stable. Now, we might have to consider the effect of any water getting into that surface and what effect that would have on the basic friction angle. But from the information we're given there, those rocks are stable. If we look at example C now, example C, again, we've got discontinuities in the rock. Those discontinuities appear within the slope. That sliding surface that's shown in red appears there at the bottom. The dip then is towards that slope. It's coming out of the slope. And if, again, we've got a basic friction angle of 26 degrees, these are clearly dipping at an angle greater than that basic friction angle, which would make these rocks unstable. These rocks will fail. Example B then, on the right, we can see there that we've got, again, discontinuities. We have a dip that may be getting towards 25 or 26 degrees. However, in this case, even though the discontinuities daylight in the slope, the dip here is into the slope. Because of that, these rocks don't have anywhere they can slide to. The force will be heading down the dip of those discontinuities, so this particular rock outcrop will be stable. But there are some perhaps other challenges here because of those joints within the rock. There may be some rock fall as a danger from this slope, but you'll deal with that, you'll engineer a solution to that in a different way than you would, say, for example C there, where the whole slope could slide away. So it gives us some indication of the type of thinking we need to undertake when we look at the examples on your worksheet. I've given you 4 different cross sections. This is our first one, section A. We have some slates here, a bit of cleavage, a bit of bedding, a bit of folding going on there. And crucially, we have a basic friction angle of the slate of 32 degrees. Make a note of that, because you'll need that when we're going to work on these slopes. Section B then has a sequence of carboniferous sediments there at its base and the Jurassic sandstone above there. The basic friction angle for this Jurassic sandstone is 35 degrees. As engineering geologists as well, can we consider, are there any other potential problems with this site? Section C has a sequence of desert sandstones and shales with some arcos there at the top. The basic friction angle of the shale here is 21 degrees. And can we think of any other potential problems with this site? Finally then, section D, we've got some carboniferous limestone, bit of quaternary till there on the south side. Are these slopes stable? And are there any other potential problems with this site? So, you've now seen details of all 4 sites. You've got the basic friction angles for some of them. What I'd like you to do now is I'd like you to work out, firstly, are those slopes stable or unstable? Secondly, are there any other potential engineering geology issues that we need to consider if we're going to dig out, excavate these cuttings? And thirdly, and this is perhaps a bit of a bonus one, what would you do about these problems? Could you engineer a solution to them? Okay, press pause on the video now and have a go at that. Okay then, let's have a look at some answers, see what you've come up with. If we start with section A, we've got a basic friction angle of this slate of about 32 degrees. We can see on the north side of this slope a dip of cleavage, which will be a discontinuity, is greater than 32 degrees. Also, the dip of any bedding in here, that's probably a bit less than 32 degrees. But the cleavage there is certainly dipping more than 32. However, despite the fact that daylight's into the slope, the dip of that cleavage is going into the slope. So the north side of this will be stable. On the south side, though, the dip of the cleavage is clearly coming out of the slope. If we measure the dip here, we get the dip to be about 30 to 32 degrees. So the south side of this slope is potentially unstable. It might be a little bit too close to the basic friction angle to be reassuringly safe. It may be that these blocks of slate may need pinning in place, for example, to prevent them moving, particularly the blocks that might separate from the vertical bedding here and slide into the cutting, particularly perhaps after heavy rain. In section B, the basic friction angle of the Jurassic sandstone here is relatively high, 35 degrees. And we can see that the Jurassic sandstone is dipping much less than that on both sides of the slope. So these slopes are both going to be stable. However, there are some other things to consider. We've got a sandstone sitting on top of a mudstone. There's an unconformity between the two. So within this cutting, there's the potential for springs. Now, clearly, it depends on the permeability of that Jurassic sandstone, which we don't know. But as an engineering geologist, we'd need to find that out. We'd need to find out what's going on with the water at that boundary between a potentially permeable Jurassic sandstone and an impermeable Carboniferous mudstone. There's another potential hazard that would have to be investigated, would have to be understood before this cutting was built. We can see that there's a coal seam beneath this area. Clearly, there's some evidence of mining. So as an engineering geologist, I'd want to know what was going on with that coal. Are there any historical records of mining? Would there be any geophysical work we could do to investigate the potential for any void space and potential subsidence of any mined coal in that area? It's important for engineering geologists to find these unknowns. So in section C, we have shales and desert sandstones, both dipping to the north. The basic friction angle here is 21 degrees. We can see that the dip of these beds is greater than 21 degrees. So that indicates there's potential instability here. On the north side of the cutting, we can see that the dip here is into the slope, so that's going to make that stable. However, on the south side of our cutting, we have some issues. The dip here is greater than 21 degrees, and we have the boundary between the shale and the desert sandstone daylighting into the slope. Now, again, we think about the potential problems we have here. A desert sandstone is likely to be porous and permeable. Shale is likely not to be. So water along that boundary could be an issue. Could explain perhaps the relatively low value of the basic friction angle. But this slope is clearly unstable. Something would have to be done, certainly with that desert sandstone sitting on top of the shale, to stop that sliding into the cutting. The weak nature of desert sandstone, it tends not to be very well cemented, would make that harder to deal with. It may be that a retaining wall would have to be built. It may be that even the slope might have to be cut back to below that bedding plane. Although you can see just how much extra material would have to be removed for that. There's another potential issue here with this site as well, because of this porous and permeable sandstone and the shale being impermeable. What's going on with the water underneath this cutting? We could have a confined aquifer here, with water in the desert sandstone underneath the cutting being under pressure. Now, if we remove the rock above that, remove some of that confining pressure, could we end up with an artesian spring going into our cutting? Could we end up with swelling of the shale into the cutting, deforming whatever we're putting in there? Again, we need to know. We need to think carefully about what's going on with the water. Finally then, section D. Here we don't really have dip of discontinuities as an issue. We've got a well-jointed Carboniferous limestone, we've got beds, we've got joints running through that, and it all seems fairly horizontal. So the rocks in this particular cutting will be stable. However, if we look at some of the wider geology around here, we have some till, which will be impermeable. And perhaps there's a river flowing over that then disappears into the ground at that swallow hole. We can then see water reappearing out the ground at a spring on the north side of this hill. As an engineering geologist, I'd want to know what's happening to that water. Where is it underground? Because if we connect The base of that swallow hole, through perhaps a smoother line than I've been able to draw there, down to that spring, that blue line I've drawn there is the potential height of the water table. Now, it may be lower than that. I don't know. But as an engineering geologist, I would need to know. If it is as high as I've shown there, which it has the potential to be, particularly perhaps in the winter, if we dig that cutting, it is going to end up as a pond. If we're digging below the water table, the hole beneath the water table will flood. So if that is the case, and I need to build that cutting in that particular location, I need to be looking at a way of maybe diverting water away from that swallow hole, of perhaps draining water out of that cutting. It does potentially create a whole series of problems for us there. Another potential issue with any engineering work done in limestone or other carbonate rock areas is the potential for cavities, for void spaces, or caves if you prefer. If we've got water passing through the limestone here, there's a good chance that that water has been dissolving limestone, expanding the bedding planes and the joints, making cave passages. So if I'm going to build something on top of these, I want to know what's down there. I want to know if there are any cavities that have the potential to subside when I start digging out above them and putting a load on top of them. So, if we think carefully about this slope stability, we can see that there's an awful lot of factors that we need to take into consideration. As well as the discontinuities, what else is going on with the other features of that rock? Its lithology, its permeability, its porosity. Crucially, what's going on with the groundwater? All of these things are going to have an impact on the stability of slopes. Now we need to look at some perhaps real-world examples of this, but that's for another lesson. I'll see you then.